In 1964, two scientists found something they weren't looking for, and it rewrote everything we thought we knew about the universe's birth. Arno, Penzias and Wilson were trying to eliminate noise from their radio antenna. Every direction they pointed it, they heard the same persistent hum. Static, interference, or so they thought. What they'd actually discovered was the oldest light in existence, radiation still traveling across space, 13 billion years after the universe began. They had no idea they'd just found proof of the Big Bang itself. But here's the question that haunted cosmologists. If the Big Bang happened, shouldn't we still be able to hear it? Not with our ears, the frequencies are far too low, but with the right instruments, sensitive enough to catch whispers from the dawn of time itself. That's where the cosmic microwave background enters the story. The CMB is the leftover radiation from when the universe was only 380,000 years old. To put that in perspective, the universe is now 13.8 billion years old. The CMB is a fossil, a time capsule, a photograph of reality when it was still in its infancy. When the universe was born, it was unimaginably hot and dense. Light couldn't travel freely, it bounced endlessly off charged particles in a blinding fog. Then, roughly 380,000 years in, something shifted. The universe cooled enough for electrons and protons to combine into neutral atoms. Suddenly, light broke free. It's been traveling ever since. That first light, that moment of cosmic transparency, is what we're detecting today. Except the universe has been expanding for 13.8 billion years. Space itself has stretched. The wavelengths of that ancient light have been stretched too, shifted far into the microwave part of the spectrum. What was once blazing visible light is now barely a whisper of radiation. So when Penzias and Wilson heard that hum, they weren't listening to random noise. They were listening to the universe's first breath. But why did this matter so much? Because before this discovery, the Big Bang was just a theory. Elegant, mathematically sound, but unproven. There was a competing model called the steady-state theory. It said the universe had no beginning, no end. It simply existed, eternal and unchanging. New matter was constantly being created to fill the gaps left by expansion. It was philosophically appealing. It avoided the awkward question of what came before. The CMB killed steady-state. If the universe had always existed, there should be no radiation signature from an ancient, hot beginning. The fact that we detected this background glow uniform in almost every direction with a temperature of just 2.7 degrees above absolute zero proved the universe had a birth. It had an origin. But the CMB did something even more remarkable. It gave us the universe's age with unprecedented precision. By measuring the radiation's temperature and properties, physicists could calculate how long the light had been traveling. How many times space had expanded? How much time had passed since that first moment of freedom? The answer, 13.8 billion years. That's our universe's birth certificate. Before the CMB, estimates varied wildly. Some said 2 billion years, others argued 20 billion. The uncertainty was enormous. The CMB narrowed it down so precisely that we now know the universe's age to within about 50 million years. Here's where it gets stranger. The CMB isn't perfectly uniform. There are tiny temperature fluctuations, differences of just millionths of a degree. These aren't random. They're the seeds of everything we see today: galaxies, stars, planets, us. In those first moments after the Big Bang, quantum fluctuations, infinitesimal jiggles in the fabric of reality, were blown up to cosmic scale by inflation, a period of impossibly rapid expansion. These tiny wrinkles became density variations. Over billions of years, gravity amplified them. A region slightly denser than average pulled in more matter, which pulled in more matter, until it became a galaxy. The CMB's temperature map is essentially a fossil record of those ancient fluctuations. When we look at it, we're looking at the blueprint of cosmic structure, the universe's birth announcement encoded in radiation. Scientists have refined these measurements for decades. In 1989, NASA launched COBE, the Cosmic Background Explorer, which mapped the CMB with unprecedented detail. Later, WMAP and Planck satellites took even sharper pictures, confirming and refining our understanding of the universe's composition, geometry, and age. These observations revealed something profound. The universe is flat, not curved, not wrapping back on itself, flat, stretching infinitely in all directions. It's made of roughly 5% ordinary matter. The stuff we're made of 68% dark energy and 27% dark matter. We can't see the last two, but the CMB tells us they are there. So we return to the original question. How did the echo of the Big Bang reveal the universe's true age and origin? The answer is elegant. The CMB is the universe's oldest message. By reading it, measuring its temperature, mapping its fluctuations, analyzing its polarization, we decoded when the universe began, what it's made of, and how it evolved. Penzias and Wilson didn't set out to discover the Big Bang, they were just trying to fix their antenna. But sometimes the most profound truths hide in the static, in the noise, in the whispers that have been traveling through the void since before Earth existed, before our sun ignited, before the first stars were born. The universe is 13.8 billion years old. We know this because we learned to listen. Subscribe for more untold stories from the cosmos. Each week, we uncover how accidental discoveries reshaped everything we know about space.